space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the Bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European service module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of 2 young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules complete, the spacecraft moves from the MPPF into the Launch Abort System facility.
We just finished fueling the spaceship and we moved it to the LASA facility, the Launch Abort System facility, to put the Launch Abort System on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the Launch Abort System works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
The sun would first stir life on our planet. Gradual shiftings and upheavals would bury creatures and plants beneath the surface of the Earth. There, they would fossilize, eventually turning into huge reservoirs of gas and coal.
Oil made possible one of the greatest inventions of history, the internal combustion engine, which gave us mastery over the air. Pollution grew around us, until one day, at last, we noticed that something had gone wrong with our once pretty world. Just in time, the satellite now gives us a view of pollution impossible to get in any other way. scientists and researchers continue to develop various technologies to cut fuel consumption through aircraft structure and engine design. Lightweight wires and electronics replace mechanical linkage. NASA researchers see vertical takeoff aircraft as commercially useful. These types of aircraft use less room for takeoff and landing and keep noise and air pollution lower than our present commercial planes. One of the most unusual and highly experimental aircraft ever tested at Dryden was the Gossamer Albatross. The Albatross was human-powered and pedaled like a bicycle. The man who designed the Albatross also built the Gossamer Penguin, the world's first flight-worthy sun-powered plane.
ERAST is NASA's Environmental Research, Aircraft and Sensor Technology program, and its mission is to develop aircraft that are capable of flying very high and very slowly, primarily to do atmospheric sampling and monitoring of the global environment.
Solar power offers some unique capability for flying in the stratosphere. The Helio should be able to stay aloft for up to 6 months at a time to function very much as an atmospheric satellite.
What's very unique to the solar-powered airplanes is that they are not polluting the very atmosphere that they're trying to take samples from, so they're ideally suited for that purpose.
These vehicles can help us attain a desirable balance between technology and nature. The stakes are high as we speed toward a challenging future.
Solar-powered aircraft don't really work well at nighttime. This is a way of compensating for the inability to get energy at night. The airplane flies off the energy provided by the laser.
This is the world's first demonstration of the application of laser energy to a flight vehicle to achieve truly fuelless flight.
NASA Aeronautics continued its green aviation initiatives. Their goal? To make air travel quieter, cleaner, and more efficient, while increasing the safety and comfort of passengers.
With this mandate to significantly lower noise and emissions and increase performance for subsonic aircraft, there will be a need to address virtually every aspect of the current aircraft configuration.
We're using a blended alternative fuel to evaluate the impact of different fuels on the emissions of the aircraft.
People have done life cycle studies to look at the carbon balance, which takes into account the amount of energy that you use in growing the plant, processing the oil. Some of the studies have shown about a 75% reduction in the amount of CO2 that you get using camelina compared to a conventional petroleum-based fuel.
NASA started investigating alternative fuels as a way of reducing the carbon emissions from aircraft, but there's other benefits of these fuels. They produce much lower levels of soot, and also they do not have sulfur contaminants.
Hopefully there will be a fairly significant return on the investment in terms of improved public health and environment.
Everything within subsonic aviation now is looking for efficiency. We're looking at structures to make aircraft lighter. We're looking at various propulsion systems in order to make them more fuel efficient. And we're looking at configurations to lower the noise impact of community noise, essentially looking at an environmentally responsible aircraft.
We really think this airplane is revolutionary. It's a big jump in technology from the tube and wing kind of airplanes that you see today. It's much more efficient. I like to say it's like a hybrid car compared to a regular car.
It's exciting to think that we're contributing to the green aircraft of the future.
The aircraft now can be programmed to have, for example, engines that are more fuel efficient. Control the engines separately and also more closely and carefully.
This is NASA's first all-electric crewed aircraft.
We can use electric propulsion systems and aircraft design in an interactive way. The wing itself is designed so that the electric motors enable extra efficiency in the wing itself.
There's several different types of airplanes that can benefit from electric propulsion. The one that's gaining a lot of interest right now is the smaller version, the air taxi type vehicle.
In doing the work of developing these systems, integrating these systems and so forth, we have helped industry along their path.
We've been able to deliver lessons learned on batteries, on how you do the power
electronics, how you build up the motors. And so X-57 really has been a pathfinder early on for electric propulsion.
The next generation of vehicles, they're going to be much greener and much more efficient types of propulsive technology.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Something has now emerged that might make even our most elegant theories workable.
Scientists developed equipment which would be able to think.
Machines that do things and make choices without human beings. That uncanny spectacle is automation.
Capable of storing, processing.
Calculations that would ordinarily take hundreds of man-hours. Unique ability to check itself on possible errors.
Cheaper and quicker and better.
Electric eyes, limit switches, servo mechanisms.
Secretary, librarian, banker, teacher, medical technician, bridge partner.
Volumes of changing data into a continuous flow of interpretations. Aladdin's lamp couldn't do more.
Jaws, loading machines, electric drills, it's all automation.
Computers have taken wing.
By the late 1960s, digital computers had become more available.
Using data about the aircraft's performance, the computers vote on the correct amount of control deflection to make in response to the pilot's stick and rudder movements.
This system could make air travel of the future smoother and safer by reducing aircraft vibration through automatic response from the computer to the aircraft controls.
We did the digital engine control. We had an early large digital computer that ran the engine and the inlet and exhaust system.
We did an integrated control study to provide digital control of the inlets, autopilot, throttle, air data, and navigation system. A digital computer here, major improvement in the capability of the airplane.
Test pilots are flying a plane without having to leave the ground. It's a new way of flight testing advanced aircraft that's both more economical and less hazardous. A research pilot in a realistically recreated cockpit on the ground, complete with flight controls, flies the remotely piloted craft using computers and television.
The airplane includes computers. Those computers take stick command and
continuously monitor what the airplane is doing and compares it to what the pilot wants the airplane to do.
The computer signals the control surfaces to not only execute the pilot's maneuver, but also to counter any attempt by the X-29 to veer out of control.
Fly up.
Yikes! No doubt about it. Couldn't get a roll on that one.
New initiative in the artificial intelligence area, and it's called aircraft automation. The technologies that end up coming out of this would be autonomous flight vehicle technology,
ERAS stands for Environmental Research Aircraft and Sensor Technology. Platforms that could fly higher and longer than the current piloted airplane, do science missions and other commercial applications.
Primarily the dull, dirty, and dangerous.
We can go all the way up to where the airplane can fly itself completely autonomously with no input from anyone on the ground.
Fly up to 50, 60,000 feet, fly a circle loop perhaps over a city, providing the capability that a satellite now does.
Now that we can fly for on the order of 8 to 10 to 12 hours, we can look at long duration processes, biogeochemical cycling, looking at carbon and nitrogen moving through an ecosystem.
To sort of kickstart a commercial UAV industry.
The technology that we've seen here in this test is what would be the foundation for a follow-on program to really address the issue of how can UAVs routinely operate in the National Aerospace System.
The primary benefit of this technology is the ability of it to adapt to the unknown, whether it be a system failure, battle damage, icing on the wing, or flying in an unknown atmospheric environment.
The aircraft may be able to be flown, but the pilot may or may not be able to find a solution to how to fly that aircraft.
Neural net control systems where the controls are going to teach themselves and keep being smarter from flight to flight.
It can reconfigure the airplane in an optimal way in order to give you the best flying qualities.
Okay.
There is no operator of the vehicle itself on the ground. Basically, the role that the human plays is more in managing the mission, an orchestra director, not the instrument player.
The vehicle will complete all the autonomous actions necessary to release the weapon optimally positioned to hit the target.
One of the next things that we'll be demonstrating in UCAV is the collaboration amongst aircraft. How do sets of aircraft interact together in almost a social form?
We're going to examine the feasibility and technical utility of actually being able to fly two airplanes or multiple aircraft in formation with each other.
Now the trick to this is to make sure that they fly in formation close enough that they can extract the advantage without obviously running into each other.
The station keeping would be fairly close proximity for hours. The workload on the flight crew would be quite high, so we started to develop autonomous algorithms to do the station keeping. So you basically would have an autopilot that you could engage.
The computers are flying the airplane without your stick input, even in the system, to allow a piloted airplane to take 2, 3, or 4 unpiloted vehicles on a long distance trip.
We're just getting started on this technology. We'll use this technology to refuel unoccupied combat air vehicles.
The basket's slightly moving. Looks like it's going high. Okay, it detected a miss and came back on its own. So I did not do anything. She's got it. She's got it. Congratulations, guys. That was fantastic.
The Autonomous Soaring Project has one simple goal, is to program a small UAV to soar in thermals similar to the way a glider pilot or birds do. It has been reprogrammed to automatically detect that it's in an updraft and then use that updraft by circling. There's a wide variety of applications for this technology to help UAVs do things like forest fire detection, police surveillance, border patrol, and weather monitoring.
If the aircraft was damaged, you don't have to necessarily just rely on the pilot to compensate and fly the airplane. Adaptive flight controls, autonomous flight controls, different things where we're using the airplane to assist the pilot.
It will take over basically the controls of the airplane as far as flight stability.
The Platform Precision Autopilot is capable of staying on a given path within about 15 feet. It allows the synthetic aperture radar system to fly over essentially the same path more than once. This obviously has some potential applicability when you're looking at Earth's surface movements, such as after an earthquake, or if you're looking at an ice pack melting.
For the F-16, we went out and tested the system and based them on actual mishap cases. It prevented every single mishap. What we're developing here is merely an aid should the pilot get distracted or disoriented. By automating it, we can take out the pilot reaction time entirely.
The computer takes full control away from the pilot for a very brief period of time, and it redirects the trajectory of the aircraft to save the human.
ADS-B is automatic dependent surveillance broadcast. It's equipment on board an airplane that transmits its position and velocity information twice per second. We are really